Hello everybody. Today we start to discuss problems from American Physics Olympiad 2010 USAPHO semifinals. This semifinal consists of 2 days. First day there were 4 problems, and second day there were 2 problems. For each day they gave competitors 90 minutes for all problems. So now problem A1. An object of mass m is sitting at the northmost edge of a stationary merry-go-round of radius r. The merry-go-round begins rotating clockwise with a constant angular acceleration alpha. The coefficient of static friction between the object and the merry-go-round is mu s. First question. A. Derive an expression for the magnitude of the object's velocity at the instant when it slides off the merry-go-round in terms of mu s, r, and alpha, and any necessary fundamental constants. Question B. For this problem, assume that mu static equal 0.5, alpha equal 0.2 radians per second square, and r equal 4 meters. At what angle, as measured clockwise from north, is the direction of the object's velocity at the instant when it slides off the merry-go-round? Report your answer to the nearest degree in the range from 0 to 360 degrees. Solution. When object moving by a circular trajectory, acceleration could be split by tangential and normal. Tangential acceleration equal to this expression, where alpha is angular acceleration and r is radius, and normal acceleration equal omega square r, where omega is angular velocity, and the angular velocity equal alpha t. So finally we have this expression for normal acceleration, and the total maximum acceleration we can count from this formula. So total acceleration, that will be mu static multiplied by g, which is equal to square root from this expression. And when we put expression from here, we can count what is the total equation for this acceleration. And now from this expression we can count what is total time when the objects start to move. That will be this expression. And now we can find what is the velocity of object when it starts to slide from this merry-go-round. That will be v equal alpha tr, which is this expression. That's the answer for the first question. For the second question, we need to count what is the total angle. For the full angle of rotation, that will be 1/2 alpha t square. And the time we already know, so we can count totally to put all these numbers. That will be about 173 degrees. But we need to find what is the direction for velocity. So it means that we need to add 90 degrees to this result. So that will be this angle, theta plus 90 degrees, which is 263 degrees, which is the answer for the question. US Physics Olympiad 2010 semifinal. Problem A. spherical shell of inner radius A and the outer radius B is made of a material of resistivity ρ and negligible dielectric activity. A single point charge Q0 is located at the center of the shell. At time t equals 0, all of the material of the shell is electrically neutral, including both the inner and outer surfaces. What is the total charge on the outer surface of the shell as a function of time for t greater than 0? Ignore any effects due to magnetism or radiation. Do not assume that B minus A is small. Solution. During all of this process, internal charge of this shell equals 0. So it means that only charge could be accumulated on internal or outer surfaces of this shell. And now suppose that in any period of time we have total charge on outside surfaces Q. It means that on internal side we have charge negative Q, and it depends from time. Now we can write the Ohm law for this disposition. In any point inside of this shell, we have Ohm law, which gives us this equation: current density equal electric field divided by resistivity. Due to symmetry, it depends only distance from the center, and we can count what is total electric field due to Gauss law. So for electric field we have this equation that total electric charge equal 1 over 4 pi epsilon 0 multiplied by total charge inside of this sphere, which is Q0 minus Q, where Q is charge on internal surface, and divided by R square. And now we can rewrite that total current will be area 4 pi R square multiplied by current density, which is 1 over epsilon 0 rho multiplied by Q0 minus Q. And now because current equal dq over dt, we can write this differential equation. dq over dt equal 1 over epsilon 0 rho multiplied by Q0 minus Q. And the last step is to split variables Q and T, and we have this equation. dq over Q0 minus Q equal 1 over epsilon 0 rho multiplied by dt. After integration we have this expression: logarithm from 1 minus Q over Q0 equal negative T over epsilon 0 rho. And finally we can express charge Q as a function of time. That will be this expression. We see that for time equal 0, charge equals 0. And after a long time, this part is going to 0 and the charge is going to Q0 on outside surface, and on inside surface that will be negative Q0. So that's the solution. US Physics Olympiad USAPHO, year 2010. Semifinals. Problem A3. A cylindrical pipe contains a movable piston that traps 2 moles of air. Originally, the air is at 1 atmosphere of pressure P0, a volume V0, and at a temperature of T0 equal 298 Kelvin. First, process A. The air in the cylinder is compressed at constant temperature to a volume of 1/4 V0. Then, process B, the air is allowed to expand adiabatically to a volume of V equal 15 liters. After this, process C, this piston is withdrawn, allowing the gas to expand to the original volume V0 while maintaining a constant temperature. Finally, process D, while maintaining a fixed volume, the gas is allowed to return to the original temperature T0. Assume air is diatomic ideal gas. No air flows into or out of the pipe at any time, and that the temperature outside remains constant always. Possibly useful information. Cp equal 7/2R, Cv equal 5/2R, 1 atmosphere equal 1.01 10⁵ Pascal, R equal 8.31 joules per mole by Kelvin. Questions. Question A. Draw a PV diagram of the whole process. B. How much work is done on the trapped air during process A? C. What is the temperature of the air at the end of the process B? D. What is the lowest pressure occurs during total cycle? Solution. So, first let's draw a PV diagram of the whole process. In point 0 we have volume V0, pressure P0 and temperature T0. And we have isothermal compression from point 0 to point 1, while volume decrease 4 times. It means that pressure increase 4 times. After that we have adiabatic expansion from point 1 to point 2. That's process B. During this expansion, temperature is going down. And after that we have isothermal expansion, process C, from point 2 to point 3. And because this isotherm has a temperature lower than process A, we will get to the point 3 with a lower pressure than in point 0. And the last process is D, that's isochoric process, during which pressure and temperature going up to point 0. That's the answer for question A. Question B. How much work is done on the trapped air during process A? During process A we have isothermal compression, and isotherm, it's a hyperbola, so we need to count what is the area under this hyperbola, and for that we just need to integrate this area, which will give us a result. Work equal number of moles multiplied by RT and multiplied by logarithm from V1 over V0. So that's the formula. Now we just need to put numbers, and we have 2 multiplied by 8.31 multiplied by 298 kelvins and multiplied by logarithm 1 over 4, which give us negative 6,866 joules. That's the answer for question B. Question C. What is the temperature of the air at the end of process B? at the end of adiabatic expansion. For adiabatic expansion, we have formula. This formula connects the temperature and volume. And gamma here, that's equal to Cp over Cv, which is 7 over 5. And now we can count what is temperature in the point 2. We already know that V2 equal 15 liters, and we need to find what is V1, which is 4 times less than V0. But V0 we can count from initial conditions. From the formula for universal gas law, we have P0 V0 equal nRT0. So from here we can find what is V0. V0 equal number of moles multiplied by R T0 over P0. So now we can put all numbers, and finally we have a result that it's equal to 0.0490 cubic meters. And now we can count what is T2 in point 2. Now we can count what is V1, that's 4 times less than V0, which is 0.0123 cubic meters. And after that we can count what is temperature T2. That will be this expression. Here we already know what is T0, V1 and V. We can put numbers, and finally temperature in point 2 equal 275 kelvins. That was answer for question C. And now question D. What is the lowest pressure occurs during total cycle? From this diagram we see that lowest pressure will be in point 3. And now we can count what is this pressure. So we can count this pressure in point 3 using again universal gas law. P3 V3 equal number of moles multiplied by R multiplied by temperature. Here we already know that V3, that's the same volume as in initial point 0. So that's 0.0490. Temperature T3, that's the same as the temperature T2, because this is isothermal expansion. So finally we can count what is P3. P3 equal number of moles multiplied by R multiplied by T2 over V0. We can put numbers, and the result will be 9.33 10 power 4 pascals. That's the answer for question D. US Physics Olympiad 2010 year, USAPHO Semifinal. Problem A4. The energy radiated by the Sun is generated primarily by the fusion of hydrogen into helium-4. In stars the size of the Sun, the primary mechanism by which fusion takes place is the proton-proton chain. The chain begins with the following reactions. First reaction, 2 protons go into element X1, positron E+, and element X2. The second reaction is proton plus element X1 going to element X3 plus gamma ray. The amounts listed in parentheses are the total kinetic energy carried by products including gamma rays. P is a proton, E plus is a positron, gamma is a gamma ray, and the X1, X2, and the X3 are particles for you to identify. The density of electrons in the Sun's core is sufficient that the positron is annihilated almost immediately, releasing the energy X. During this annihilation reaction, electron plus positron go into two gamma rays. Subsequently, two major processes occur simultaneously. The PP1 branch is the single reaction. Two elements X3 go into helium-4 plus two elements X4, which releases an energy Y. The PP2 branch consists of three reactions. First reaction is element X3 plus helium-4 go into element X plus gamma ray. Next reaction, element X5 plus electron go into element X6 plus element X7. And last reaction is element 6 plus element 4 go into two helium-4 particles, where Z is the energy released in step 6. So, questions. Question A. Identify X1 through X7. X2 and X7 are neutral particles of negligible mass. It is useful to know that the first few elements in order of atomic numbers are hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Question B. The mass of the electron is 0.51 megaelectron-volt per c square. The mass of the proton is 938.27 megaelectron-volt per c square, and the mass of the helium-4 nucleus is 3727.38 megaelectron-volt per c square. Find the energy released during the production of one helium-4 nucleus, including the kinetic energy of all products and all energy carried by gamma rays. Question C. Find the unknown energy X and Y above. Question D. Step 6 does not proceed as follows because there is insufficient energy. X5 to X6 plus positron plus X7. What constraint does this fact place on Z? And the question E. In which of the reaction steps is the energy carried by any given product the same every time the step occurs? Assume that the kinetic energy carried in by the reactants in each step is negligible, and that the products are in the ground state. Solutions. Let's check the first reaction. We have two protons going to X1 plus positron plus X2, where X2 is known as a particle with a negligible mass and zero charge. So in the beginning we have total charge is plus 2 because two protons, and total baryon mass is 2, and during this reaction these numbers must be conserved. On the right we have positron with a charge positive 1. It means that particle x1 must have a charge positive 1, and also it has a mass of 2 baryons, so which is hydrogen 2. And also we have lepton number is conserved. It means that number of electrons plus number of neutrino minus number of positrons minus number of anti-neutrino must be conserved. In our case, on the left we have 0 lepton number, and on the right we have 1 positron. x1 is 0, so x2 must be negative, and because it's not electron, it must be neutrino. So that will be electron neutrino x2. So we just identify element x1 and x2. Now let's go to second reaction. Here we already know what is x1, and we can rewrite this in form of this one. We have proton plus hydrogen 2 going to x3 plus gamma ray. So here on the left we have a total charge is 2, and total baryon number is 3. x3 must be helium 3 with a charge positive 2 and baryon number 3. Now let's go to reaction 4. In this reaction we already know that x3, that's helium 3. Then let's rewrite it. On the left we have 2 particles helium 3 with a total mass 6 and charge 4. And on the right we have helium 4 with a mass 4 and charge 2, plus 2 unknown particles x4. But these 2 particles must have a charge positive 2 and mass 2. So it means that x4 has mass 1 and charge 1, which is just proton. Now let's go for equation 5. Here we already know x3, which is a helium 3, and let's rewrite it. On the left we have helium 3 and helium 4, which together have mass 7 and charge 4. And on the right we have gamma ray, which is nothing, and particle with mass 7 and charge 4, which is beryllium 7. Now let's go to equation 7. We have unknown particle x6, and we already know that x4 is proton. Let's rewrite it. So on the right we have 2 particles helium 4, which have total charge 4 and mass 8. And on the left we have proton plus unknown particle. Proton has charge 1 and mass 1, so it means that particle x6 must have charge 3 and mass 7, which is lithium 7. And now let's go to reaction 6. Here we already know what is x5 and x6, and let's replace them. On the left we have beryllium 7 with a total mass 7 and charge 4, plus electron with a charge negative 1, so total is charge 3. And on the right we have lithium with a charge 3 and mass 7. So it means that particle x7 has a neglectable mass and charge 0. And again we need to use lepton numbers. So here we have from the left we have electron, so it means that x7 must be electron neutrino to save a lepton number. So we just identified all 7 particles, which is the answer for question A. Now when we count all these particles, we can put them in these reactions and get a regular view for reactions, which will help us to answer for next questions. Question B. The mass of electron is this one, the mass of proton is this one, and the mass of the helium-4 nucleus is this one. Find the energy released during the production of one helium-4 nucleus, including the kinetic energy of all products and all energy carried by gamma rays. First, we can rewrite the reactions which are creating this helium-4 nucleus. That will be 4 reactions. First one, second, third, and fourth. When we combine them, on the left we can put all initial components, and on the right all final components. Initially we had 6 protons and 2 electrons, and we got 1 helium-4 particle and 2 protons, also 2 neutrino and several gamma rays. Now in this reaction we can cancel 2 protons to count energy. That will be this one. From here we can count what is the energy difference, because initially we had 4 protons and 2 electrons, and we got 1 helium-4 nucleus, and other energies we need to count, which include all kinetic energy for products plus 2 neutrino plus several gamma rays. That would be this equation. We had 4 mass of protons and 2 mass of electrons, and we got 1 mass of helium-4 nucleus plus energy which we need to count. So from this equation we can count that E equal 26.72 mega electron volts. That was the answer for question B. Question C. Find the unknown energies X and Y above in reactions 3 and 4. Solution. For reaction 3 we have a reaction of annihilation, positron and electron, and they are going to gamma rays. Total energy will be just mass of these particles, which is 1.02 mega electron volt. To find what is energy Y, we see that this energy, it's a kinetic energy for helium-4 plus 2 protons. So it means that we need to count what is total energy going to neutrino, gamma ray, and gamma ray here, and gamma rays here, and we need to do them twice because we have 2 particles here. And if we add Y, we will get our previous answer for 26.70 mega electron volts. So that will be this equation. So 0.42, that's energy for neutrino in first reaction, 5.49, that's energy for gamma ray in the second reaction, 1.02, that's energy for annihilation in third reaction, and we need to do them twice, and we will add kinetic energy during reaction 4, and we will get total energy counted in question B. That was 26.72. Finally, we will get Y equal 12.86 megaelectron volts. That was final answer for question C. Question D. Step 6 does not proceed as follows because there is insufficient energy for this reaction. What constraint does this fact place on Z? First, let's rewrite this reaction in known form. Solution. The forbidden reaction produces an energy of Z minus 2 times 0.51 megaelectron volts, as it differs from the naturally occurring one by the consumption of one fewer electron and the production of an additional positron. Since it is forbidden, we know that Z minus 2 times 0.51 megaelectron volt less than 0. In other words, Z less than 1.02 megaelectron volts. Question E. In which of the reaction steps is the energy carried by any given product the same every time the step occurs? Assume that the kinetic energy carried in by the reactants in each step is negligible, and that the products are in the ground state. It's well known that if in the result we have only 2 products, we can use energy conservation and momentum conservation to count what is final energy for these 2 products, and this problem is solvable. But if we have more than 2 products, 3 and more, we have a big spectrum of possibilities. We have only 2 equations, and we have many variables. So it means that in our case we have only choice 2, 3, 5 and 7. They have 2 products. So this is the answer for question E. 2, 3, 5, 7. US Physics Olympiad, year 2010, USAPHO, Semifinal. Problem B1. A thin plank of mass big M and length big L rotates about a pivot at its center. A block of mass M small, much less than M big, slides on the top of the plank. The system moves without friction. Initially, the plank makes an angle θ0 with the horizontal. The block is at the upper end of the plank, and the system is at rest. Throughout the problem, you may assume that θ much less than 1, and that the physical dimensions of the block are much smaller than the length of the plank. Let x be the displacement of the block along the plank, as measured from the pivot, and let θ be the angle between the plank and the horizontal. You may assume that the centripetal acceleration of the block is negligible compared with the linear acceleration of the block up and down the plank. Questions. Question A. For a certain value of θ0, x equal k θ throughout the motion, where k is a constant. What is the value of θ0? Express your answer in terms of big M, small m, and any fundamental constants that you require. Question B. Given that theta 0 takes this special value, what is the period of the oscillation of the system? Express your answer in terms of big M, small m, and any fundamental constants that you require. Question C. Determine the maximum value of the ratio between the centripetal acceleration of the block and the linear acceleration of the block along the plank. Writing your answer in terms of small m and big M, therefore justifying your approximation. Question D. Count what is kinetic and potential energy of the system in any particular moment. Solutions. Question A. For a certain value of theta 0, x equals k theta throughout the motion, where k is a constant. What is the value of theta 0? Express your answer in terms of big M, small m, and any fundamental constants that you require. So first let's write equations for motion, for block and our plank. For block in any particular moment we have this equation that mass multiplied by acceleration equal negative mg multiplied by sine theta. For rotation of our plank we have equation that I alpha equal negative mg x cosine theta. Now because theta is always much less than 1, we can rewrite this equation in form of this one, that the acceleration of block equal negative g theta and 1 over 12 big M L square alpha equal negative mg x. Now because we expect that our motion is synchronized, it means that oscillation of this block same angular frequency as rotation of this plank, so we can write this harmonic motion equations. So we assume that the theta starts from the top position. It means that theta equals theta 0 cosine omega t, and now we can assume that block starts with highest position. It means that x equals L over 2 cosine omega t, and our plank starts from angle theta 0, and equation will be theta equal theta 0 cosine omega t to synchronize our motions. And now we can count what is the angular acceleration of this motion and what is linear acceleration of motion of this block. We just need to take a second derivative from this expression by time. So we have expression for angular acceleration, this one, and we have expression for linear acceleration of the block is this one. And we can insert these values to this and these equations. So we have this and these expressions. And now we can count what is omega square here and what is omega square and equalize them. So from this equation we have omega square equal this expression, and for this equation we have omega square equal this expression. After equalizing them we have expression for theta 0. That's this one, and because small m much less than big M, we can conclude that theta 0 is small enough. So that was answer for question A. Question B. Given that theta 0 takes this special value, what is the period of oscillation of the system? Express your answer in terms of big M, small m, and any fundamental constant you required. So here we already have expression for omega square, and we can put this theta 0 here. Now we can find that omega square equal this expression, and from here total period will be this expression. So that's the answer for question B. Question C. Determine the value of the ratio between the centripetal acceleration of the block and the linear acceleration of the block along the plank, writing your answer in terms of small m and big M, therefore justifying your approximation. Solution. To solve this question, we need to leave these expressions. And now let's count what is centripetal acceleration. In our case, centripetal acceleration for our block equal this expression. That's the first derivative from angle by t square multiplied by distance x, so which is given us this expression. Linear acceleration. For linear acceleration we have this expression. Now we need to divide this centripetal acceleration by linear acceleration, which will give us this answer. That's 3 small m over big M multiplied by sine square omega t, which is always very small. So that's the answer for question C. Question D. Count what is kinetic and potential energy of the system in any particular moment. Let's count what is kinetic energy. That will be kinetic energy for linear motion for our block, and rotational energy for plank. That will be this expression. That's 1/2 mv square for block plus 1/2 I omega square for our plank. And we can count what is dx over dt. We already did this. And what is d theta over dt. After counting, we can put these expressions. This is our kinetic energy for block, and this is our rotational kinetic energy for plank. We can rewrite it in form of this one, and because theta 0 equal this expression, we can put it here and find final expression for kinetic energy. That will be this expression, and to simplify it, we can use theta 0 to express it like this one. Now let's count what is potential energy for the system. That will be just potential energy of this small block. Potential energy equal mgh, where h approximately equal x multiplied by theta. And we can insert expression for x and theta here. That will be this one, and finally got this one. So we have for kinetic energy this expression, and for potential energy this expression, which is quite understandable, because total energy equal kinetic plus potential, which is this one. And if you look at this formula, that will be potential energy in the initial position, where theta equal theta 0. So that's the solution for question D. US Physics Olympiad year 2010 USA PHO Semifinal. Problem B2. These three parts can be answered independently. Part A. One pair of ends of two long parallel wires are connected by a resistor. Resistance equal 0.25 ohms. And the fuse that will break instantaneously if I0 current through it equal 5 ampere of current passed through it. The other pair of ends are unconnected. A conducting rod of mass m, small, is free to slide along the wires under the influence of gravity. The wires are separated by L equal 30 centimeters and the rod starts out distance A equal 10 centimeters from the resistor and the fuse. The whole system is placed in a uniform constant magnetic field of B equal 1.2 Tesla, as shown in the figure. The resistance of rod and the wires is neglectable. When the rod is released, it falls under the influence of gravity, but never loses contact with the long parallel wires. Questions. 1. What is the smallest mass needed to break the fuse? 2. How fast is the mass moving when the fuse breaks? Solutions. First, what is the smallest mass needed to break the fuse? Let's count it. When we have a rod which is free to fall under gravity, it will start to accelerate, but because it's moving through a magnetic field, due to electromagnetic induction, there will be EMF created to decrease this acceleration, and there will be current through this rod which is going to the direction to reduce this change of magnetic flux. So it means that from a magnetic field we will have a force acting in opposite to motion way. And we can just write this equation that after a certain time this rod will reach the terminal speed. We will have mass multiplied by g, which is force of gravity, must be equalized by force from magnetic field, which is BIL. In our case, maximum current is I0, so it means that we can count what is mass needed to break this fuse. That will be this one. So mass equal magnetic field multiplied by length of rod multiplied by maximum current and divided by g, gravity acceleration. So that will be finally 0.18 kilograms. That's the answer for first question in this part. Second question. How fast is the mass moving when the fuse breaks? Now let's count what is the speed. When this rod moving with some sort of speed, that will create EMF due to change of magnetic flux, and this EMF could be counted by this way. EMF equal change of magnetic flux through a certain time. In our case, magnetic field is constant, so that will be change of area under certain of time, and that will be just magnetic field multiplied by length of this rod multiplied by speed of this rod. We know that EMF equal current multiplied by resistance. In our case, we know that maximum current is I0 and resistance is 0.25 ohms. So now we can count what is speed. Because from the other hand, EMF equal I0 multiplied by R, we have for speed this equation. That's equal I0R over BL. When we put numbers, we will get 3.47 meters per second. That's the terminal speed of this mass. Part B. A fuse is composed of a cylindrical wire with the length L and radius R much smaller than L. The resistivity, not resistance, of the fuse is small and given by rho fuse. Assume that the uniform current I flows through the fuse. Write the answer below in terms of L, R, rho F, I, and any fundamental constants. First question. What is the magnitude and direction of the electric field on the surface of the fuse wire? Second question. What is the magnitude of and direction of the magnetic field on the surface of the fuse wire? Third question. The Poynting vector S is a measure of the rate of electromagnetic energy flow through a unit surface area. The vector gives the direction of the energy flow. Since S equal 1 over mu 0 multiplied by cross product electric field by magnetic field, where mu 0 is the permittibility of free space and the E and B are electric and magnetic field vectors, find the magnitude and the direction of the Poynting vector associated with the current in the fuse wire. Solution. Suppose that our fuse is going inside of this page and the current going inside of this page. It means that the electric field must go inside of this page. And we can write equation for Ohm law for this fuse. Potential difference between ends of this fuse, U equal current multiplied by resistance of this fuse. But resistance equal resistivity multiplied by length L and divided by area of cross section, which is pi r square. And from this formula we can find what is electric field. That will be potential difference divided by length. And finally we have electric field equal current multiplied by resistivity of this fuse and divided by pi r square. Now magnetic field we can count from Ampere law. If we have a wire with the current I and the radius r, on the surface of this wire we have magnetic field equal this expression. And if current going inside of this page, magnetic field is going clockwise. And from these two directions, electric field going inside of page and magnetic field going clockwise, we can count what is the magnitude and the direction for Poynting vector. That will be this expression, 1 over mu 0 multiplied by cross product. In our case, electric field and magnetic field, they are perpendicular to each other, so it means that we can count full cross product like this. And due to vector cross product direction, we have direction for this Poynting vector is going inside of this fuse. So it will get hotter during the time. So we just answered for all three questions for this section B. Part C. A fuse will break when it reaches its melting point. We know from modern physics that a hot object will radiate energy approximately according to the blackbody law at power equal sigma AT power 4, where T is the temperature in Kelvin, A is the surface area, and sigma is Stefan Boltzmann constant. If T fuse equal 500 kelvins is the melting point of the metal for the fuse wire with the resistivity ρ equal 120 nano-ohm by meter, and I fuse equal 5 ampere is the desired breaking current, what should be the radius of the wire R? Solution. So from one point we can count what is total power which is absorbed by this fuse from pointing vector. That will be P equal pointing vector multiplied by side area of this fuse. From other point we can count what is power emitted by this fuse as a black body radiation. That will be this expression. So now we just can equalize these powers. So this side area is cancelled, and we have equation that pointing vector which we count earlier equals sigma T fuse power 4. From here we can count what is the radius of this wire. That will be this expression, and after when we put numbers we can count what is radius. That will be 0.35 millimeters. That's the answer for part C.